Hey guys, this is our final team teach. I'm Kim.
And I'm Katie. Let's jump right in. So, Kim, whenever we started the semester, we started with graphs. And with those graphs,
hmm
we were given many explanations and we were asked to match those explanations to the appropriate graph. So, we can
Yes.
start at the top and we will try to match those graphs to the appropriate graph. So the first one says, it was the one about the elevator. And it says,
hmm
to explain a graph to correlate with the function of the height of the elevator stopping at each floor on the way up. So if you were just
hmm
to guess by looking, which one would you think is the appropriate one?
Well, looking at the first graph, I can see that if I were to, think about an elevator, I think about how many levels and floors that a building has that would have an elevator in it. So the first graph, I would go ahead and mark that out because that doesn't look like it has levels of floor. It actually looks like it's slowly decreasing in some way. So I would just mark that one off.
Okay.
The second one, I would almost say I could, list that as a possible chance, but honestly, looking at it, again, like I said, it just doesn't look like levels of floors. It
Mm-hmm.
honestly looks like the elevator would be going sideways and steadily decreasing rather than up and down the y-axis.
Mm-hmm.
So I would mark that one as well. But looking at the last one, I would definitely pick that one as my choice because looking at it, it does have certain levels and it does have like a time expansion. Yeah, and it's definitely increasing as well. So,
Absolutely. Okay, so the next one is to explain a graph to correlate with the function of the height of a ball bouncing when it's dropped from a table. So for that one, I would say it matches the first one, only because we've already talked about the
mhm,
graphs. So we know that it starts off high, and then when that ball is dropped
mhm,
onto the table, and then it bounces and continues to bounce. And then it almost looks, if that graph was to continue, it almost looks like it would bounce a little bit long, well, it'll bounce a little bit longer, and then it would eventually just go into a line and stop.
just yeah, of course, it would
Mhm,
eventually end.
mhm.
I definitely agree with that because just looking at the other one, it doesn't even look like you would drop it from a table, and it doesn't have any bounce to it. It just looks like it's decreasing.
Mhm. So through
So I
process of
agree with your choice.
elimination, I would say that this is the
Mhm,
last one. So for that, I would say that it's the last one because this was the one about the gas. Whenever
mhm,
the driver fills the tank on the cross-country road trip. And so I would say this is about halfway full, and then he drives across country, or he starts to drive across country. And
yes,
whenever it hits this low point, I would say that that's when the gas is out in the car. He's at the gas station and he puts gas in his car and he fills it up. And then that's
yes,
the full tank of gas. And then he drives, and as he drives, it lowers the, of course, gas
mm,
in the tank, um,
yeah,
meaning that that would be. So if he was to fill up his car again, then it would just go, of course, up,
all the way back at the
and
top.
then it would go down, and it would just go so on and so forth.
So looking at the half tank, it actually looks like, that would be the constant, um,
Mhm.
that would be the constant line of the graph because you see half of that's just decreasing
Of
as it
course.
would, using the
Yeah,
gas. So,
absolutely. So taking a look at this, what is a function? So for this, it's kind of one of those plug and plays that we've
mhm.
discussed. Do you want to explain the graph a little bit and how it works?
Yeah, sure. So, when just talking about functions, it really just has like an input and an output.
Mm-hmm.
So we see here, let me get my annotation tool. We see here that we're giving our input, which is the x value. So that means we are looking for our y value. So y is what? Oops, sorry. Y is what? So looking at this, we see, and I'm going to point something out that you actually pointed out to me in our previous team teaches that f of x actually just is a simple, f of x is just a bigger term for simple term y. So,
Yes.
because it wouldn't make much sense if we're inputting x and getting x.
Mm-hmm.
So our functions, these are our three functions. And like you said previously, we can look at these as their own little graphs or charts, actually, tables. So we have all these x's, and we're plugging those in here
Mm-hmm.
to get the output of all of our y's. So really, it's just an input to get the output. So it's really simple. All you're really
Mm-hmm.
doing is plug and chug in. So,
Absolutely. All right.
any input on that?
No, I think that you explained it perfectly. I like, of course, the little illustration that we have here that it's kind of
Mhm.
that function machine, and you input something and then
Yeah.
get the output. So I think that's a great illustration.
Well, thank you.
So there are multiple methods to find the slope. So some that we talked about during the semester was, of course, that rise
Mhm.
over run. And then, of course, putting it into slope-intercept form, which is
Of
mx
course.
plus b, and then using to find lattice points. So whenever we look at rise over run, when I hear the word rise, I think of like someone
Mhm.
rising, climbing a ladder, and then once they get to that flat surface, then they can run. So the rise of the run.
Yeah.
So with that, I would say that we go up and we're rising. So we could look at these as like steps on the ladder. So we're
Mhm.
stepping up 1, 2, 3, 4 steps of the ladder. And then how would we calculate the run?
So as you just explained, so our rise is actually our y value and our run is our x value. So
Mm-hmm.
as you said, our y value is going up. So run is actually going to be the distance on the x value. So the same way you just did, we would count that as 1 and 2. So we have 1, 2, and you would put 2 on the denominator and you would just simply divide that and you'll get our slope is 2. And
Absolutely.
there's also other ways to do it. Like you said, we could do self-intercept form or we could use lattice points. But I
Mm-hmm.
think we should point out, like especially like on this teach, which we have pointed it out before, our lattice points is not something we expect our students to know by looking at the graph, but actually looking at our data table, our
Mm-hmm.
information. Because right here, this is y1, this is x1, x2, x3, and we'll use those to find our slope-intercept form as well.
Absolutely. All right. So moving on to our next one, we've talked about many, many, many different kinds of lines over the
Hmm.
semester. But just to hit on a few of them, we can talk about
Yeah.
intersecting, perpendicular, and parallel.
Hmm.
So with the,
Um,
go ahead, you can start with intersecting lines.
oh, you're fine. You're fine. I kind of just think of intersecting lines as they at least have to have one point where they cross and meet each other.
Hmm.
So kind of think of it like an intersection almost. Like
Hmm.
two ways can two places can be crossed, and they're also you see that these lines are also not ever touching again but that one time. So
Yes.
that's why I said at least cross one time to
Hmm.
be intersecting lines.
Hmm. So,
Um,
taking a look at the parallel lines, I would say
mhm,
kind of one of my tricks to remembering which is which, parallel lines, it kind of gives us a hint because whenever you look at the
mhm,
word parallel, it gives you two lines that are parallel or two L's that are parallel to each other.
yeah,
So you could draw arrows on the top and bottom to help yourself
mhm,
remember that those parallel lines go on and on and on and on forever without ever touching. And that's what those arrows mean. And of course, them being
of
perfectly
course.
horizontal to each other.
So parallel lines never ever touch, correct?
Yes.
So it's a good differentiation between intersecting lines and parallel lines. And I love that
Yes.
you pointed out like parallel lines give you in the answer in parallel. So
Yes.
um just to like hit a little bit on perpendicular lines, I
Hmm.
kind of like think of a four-way when I look at this image
Hmm.
because we all have to cross to the same area, but they're not actually they're not parallel and they're not intersecting lines. And I believe that they're not intersecting lines because as you can see in intersecting lines, they're going somewhat the same direction, even though they'll never touch again. But
Yeah.
as as for like perpendicular lines, they're perpendicular of each other. So we would have like a right
Hmm.
triangle, 90 degrees,
Uh-huh.
right angle,
Right angle.
yeah,
Yes.
right angle every single way. So there would be no lines like that going through it. It would have to be kind of like a four-way is how I think of it.
Absolutely. All right. Well, that's a great visual. I didn't think about, the 90-degree angles,
Yeah.
forming it as perpendicular. So, All right. So then we talked about, finding the negative reciprocal. And for that, we call that the flip and switch method.
Mm-hmm.
And so for that, we have, of course, A over B. And what we're going to do is we're just going to literally flip the numerator and the denominator.
Mm-hmm.
And then once we flip those, we have to remember to, of course, switch the sign. So there's an
Mm-hmm.
understood positive sign, of course, in front of the A and B,
Mm-hmm.
but we have to switch it to a negative symbol whenever we flip, of course, the reciprocal.
Mm-hmm. Of course. So if we were to start with like a negative A over B, we would end up with a positive B over A, correct?
Absolutely.
If we were just to find the reciprocal
Yes, and that's
in the
all
means,
the
I mean, like that.
reciprocal is doing.
Okay.
It's flipping and switching. It's a real simple,
Oh,
you just flip and switch. Mm-hmm.
hmm that's
All
pretty
right.
fun.
So what about tangent lines? So tangent lines is kind of a fun one because, or it can kind of be a little trickery actually, because we see, of course, here at first, this right here, that's going to be our tangent line because it just
Hmm.
touches that
Yeah.
straight line. But if you look a little further down, we have it labeled that it is not a tangent line, and it's not a tangent
Hmm.
line right here because it's now a
Intersecting
intersecting
line.
line.
And
Absolutely.
we just learned
Intersecting
about
line.
that.
Yes, ma'am. So, just
So if,
remembering that,
oh, you're
it's
fine,
always
sorry.
a building. No, it's fine. That it's, of course, always like building blocks on each other.
Mhm.
And that's why we started the semester, of course, with that information and we built upon it.
Of course. So you're saying that tangent lines are just where they barely touch, but not
Mhm.
actually intersecting.
Intersect.
So
Yes.
that's the difference between those two.
Yes. And I have
I think
another
that's a great
example of
visual.
that later on in the presentation,
Mm.
actually here. So that great example of it is here, of course, on our circle. We have that it just touches that line. That would be our tangent line. It's just touching.
Of course.
So this problem was whenever we find the radius of a circle. So we of course know
Mhm.
that is the center of the circle, and we see that it's of course on the center of the graph just for simplicity purposes for this one. So, but it could
Yeah.
be anywhere, the center of the circle, wherever it is on the graph.
Mhm.
So for here, it's going to be 0, 0 is our points for it. And we see that it goes over 9.5 and it goes up 9.5. So if we were to draw our line down here, if it was straight, then we would see that the next point is of course that 9.5, and same for over
Mhm.
here. So our ray or radius is sometimes referred to as the ray is 9.5
Mhm.
throughout the entire circle.
Mhm.
All right. So jumping right along, what about corresponding angles?
See, I like that we use this image, especially during the team teach, because as you pointed out in our team teaches, we love to have like a visual representation of, images. So the
Mhm.
color here would be like our visual. So we could see
Yes.
that 7 and 3 are corresponding together, 6 and 2, 8 and 4, and 1 and 5. So talking about corresponding angles, we're really just talking about congruency. So meaning that every angle that is congruent or corresponding to each other have to be the same measurement. So we have
Mhm.
another image here that explains it a little bit more in depth. That was like on our homework question.
Mhm.
So we see that 9 would be congruent to 61, 2 would be congruent to 63, um, uh,
7 to 12, 8 to
4 would be
11.
congruent to 3.
Mhm.
Mhm.
So pretty
Yes,
much
you
just
see
like
what I'm
the
talking about.
opposite. Absolutely.
Of
So,
course.
and here
And
was,
we have our little chart here.
absolutely.
Sorry.
No, that's fine. Great minds think alike, don't they? All right. So, how would we find the measurement of an angle? So
Oh.
to do that, that's fine. So to do that, we think of the types of angles that we have. So we have our
Of
cute little
course.
angle, and that is always going to be less than 90 degrees. our 90-degree or right angle is always going to equal 90
Mm-hmm.
degrees. The obtuse angle is
Of
always
course.
going to equal 130 degrees. Well,
Of
it's
course.
between 90 and 130.
Yeah. Yeah.
Our straight line, it equals 180. The reflex angle is kind of a
Mm-hmm.
tricky one because it can sometimes be disguised as the obtuse angle.
Yeah.
You just have to see which way the opening is, meaning like which
Yeah,
way
of
that
course.
circle is. But that's going to be
Mm-hmm.
an angle that measures between 180 and 360. And then our
Yeah.
full angle is going to be that is exactly 360 degrees around. So a
Mm-hmm.
full angle, a full circle.
Mm-hmm. So with that being said, just thinking about just thinking about our straight angle and how it's 180 degrees, we see that it's a straight line, but not necessarily a straight line, it's half of a circle. And then
Mm,
our full angle would be technically a full circle around.
Uh-huh.
So finding the measure of the angle for this problem, I would start by labeling A, B, and C, just
Mhm.
because, I'm always I mean, all of us, I feel like we're always about labeling first before
Yes.
trying to solve the
Yeah.
unknown. So we could solve, like you said, we know that this is adding up to 180 degrees.
Mhm.
So what we would do is add 64 plus 45. And let me double check that real quick because 64 plus 45, and that gives us 109. And then that would actually equal our exterior angle right here. And I'll go into a little bit more depth about that. Um, but what we would do is do 180
Mhm.
minus 190. Might be a little bit messy right there. 180 minus 190. And then that would give a, oh, sorry, 190. 109. Why
Yes.
didn't you correct me?
Oh.
180 minus 109. Which is 71. And so our angle C would be 71. I'm like, why did I get that? So
That's
what I
fine.
was gonna say, like if we're so what I was gonna say, if we have either one of these angles right here, at the 109 and the 71, we could find the other because
Yes.
as you can see, we got this exterior angle by plugging in the sums of 64 A and B, 64 and 45.
Mhm.
So I mean, it's pretty fairly simple. But
Absolutely.
there's different ways to solve it in different methods.
Yes.
Sorry, I didn't mean to mess up there.
No, you're fine. You're fine. Mistakes are just learning opportunities. So,
Yeah.
um, so what are complementary and supplementary angles? So we know that complementary angles are angles that add up to be 90 degrees. So when
Mhm.
something that I don't believe we covered yet in this, I know we've talked about it before, is that of
Yeah.
course our 90 degrees, we have this secret code in math. And that
Mhm.
secret code, one of the many, is that little square right there that I just kind of butchered, redrawing, um, is this little square right here is
Mhm.
a code for 90 degrees. So we don't even have to use our protractor. We just know that by looking at it that this angle equals 90 degrees. So a complementary angle, we know that it's two angles that are put together and together they equal 90.
Of course.
Whereas a
Of course.
supplementary angle, they add up to be 180 degrees. So we
Mhm.
can add those two angles together, and if we did, then we would know that they add up to be 180.
Of course. So with that being said, we know what complementary and supplementary angles are, but now we need to learn how to find them, which we already know what they add up to be, but it's still good to know the math and try to do all that. So a supplement angle, all you would have to do is subtract the given angle from
Mm-hmm.
180 because like you said, supplement angles add up to be 180 degrees. So our given here is 43 degrees. So I'm just going to put that right there because it would make more sense for the smaller angle to be 43 degrees. So all we would have to do is do 180 minus 43, and then that would give us 37 degrees. I am full of mistakes today. I'm sorry.
You're fine.
Um, So that one was pretty easy. And as you said, like complementary angles are adding up to be 90 degrees. And
Mhm.
here's your little hint right there, like you said, our little square. And I wouldn't even call that cheating because that is a good thing to know because you
Yeah,
would just be
it's
like, oh, I
secret
know that adds up
code.
to be 90 degrees. Yeah,
Mhm.
for sure. So our given here would be 43 degrees. So let's label 43 degrees here. And again, so what would we do? We would subtract 90 degrees from 43 degrees. And the reason why it's 90 this time is like you said, complementary angles add up to be 90, not
Yes.
180. So we would subtract that together and get 47 degrees. So if we have one, we could find the other.
Yes.
So yeah, it's pretty self-explanatory. It's pretty easy, but it's a good thing to go over things like this, not only to know what these angles are, but how to find them.
Absolutely.
Um,
All right. So the next thing we can talk about is, of course, our concave and convex polygons. So with
yes.
that, during the semester, we had a little illustration that we used, and that was our
Yeah.
little bear. And our little bear is tired and he's ready to go hibernate in his cave. So
Mhm.
in his cave, we see the concave. So our little bear
Mhm.
can go in right here, right? He goes into the cave and he sleeps in here and he's got his warm little berries
Yes.
and everything. He sleeps through the winter. So that is going to be a concave polygon, a concave shape.
Of
But
course.
if my little bear comes out and he says, oh, I want to go to a new cave, right? So we can walk
Yeah.
all the way around this shape and we see that there's nowhere to enter. And that would
Mhm.
be a convex polygon or a convex
Mhm.
shape. And something kind of fun that we could do to help us remember that as well is we could put little arrows on the
Yeah.
X, and we know that all of the angles,
Yeah.
all of the vertices, they point outward.
Yeah, and that's what I was gonna point out is that we see, like you said, cave, you think about a cave. When you
Mhm,
see vex, I think of vertex or vertices. So when we're
mhm,
talking about vertexes and vertices, all the corners touch and meet. So with these
mhm.
corners, they're touching and meeting inside concave, and these are actually, called our vertices, our points. They're pointy.
Uh-huh.
Um, so I don't know, I just thought about it a little bit differently. But I like
Absolutely.
that you put the arrows on the X because it makes more sense for it. You know what I mean? It tells
Yeah.
you a visual representation of
Mhm,
it's not gonna
mhm.
concave, it's,
Well, you never know
convexing,
what's gonna
so
stick. You never know what's gonna stick for students.
yeah.
So having, different teachers explain it different ways, you never
Mhm.
know what's gonna stick. So you might
Yeah.
as well, why not collaborate with your
Yeah, of
teachers?
course. Of
All right.
course.
So let's take a look at this question together.
Mm,
Let's start off though by just immediately looking at the shape and what do we
mhm.
think this shape is, convex or concave?
I think it's concave because looking at it, we know with concave shapes, we know if it at least concaves in one time, the
Mm,
image is concave because we could see where these little angles are telling us it's concaving basically. But
mhm,
we do also see, some convexing angles, but that doesn't make this image, convex. It makes it concave because of these concave images right here or angles right here.
mhm.
Sorry about that.
Absolutely.
um, but the thing about this question is, looking at the question, we see what is in and what is y. And we talked a lot about this going over our two teachers because we always want to tell our students to label what they know first
Mhm,
before trying to solve any kind of problem. So we see our equation right here, n minus 2 times 180.
mhm.
Um, we don't know what n is, so how would we know what to put inside of these parentheses? So what does n equal?
So
Well,
n is
um,
going to equal the number of sides. So all we would need to do is count the number of sides. So we have one,
of course.
two, three, four, five, six, seven, 8 sides.
Yes.
So n
So,
equals 8.
and then y is telling us that, we see we have our y's next to our, we have what do you think of when you have, just learning off past experience growing up in, school? Um, what have your teachers always told you about a letter next to a number or a variable next to a number?
Well, we want to separate it.
Well, thinking about like 3y, when they're next to each other, that's an understood 3 times
Oh, yes.
y.
Yes,
Is
we'll
what
multiply.
I was always told.
Gotcha.
Well, yeah, yeah, yeah. So
Eventually,
what
we'll
does y
separate
do?
them. Mhm.
Yeah, of course, of course, of course. So that's, just think about when we're first starting, what does it mean to have, a
Mhm.
number next to a variable? That's
Mhm.
what I was trying to get at. Like
Gotcha.
we always think about, it's mean multiplication. So
Mhm.
y is 20, so we would just simply plug in 20 for y for every one of these um for each one of these angles. So we would do 3 times 20, and that would give us this angle right here, and I could do that real quick. Oh, it's 60, sorry. So this would be 60 degrees, and and if that's 60, this side would be 60 because, like we said, talked about earlier, it's a corresponding angle.
Mhm.
So
Absolutely.
right here and right there would be 60, but we could do that to solve all of these angles here, but
Mhm.
clearly we're just trying to refresh, not do it.
Absolutely.
Sorry.
No, no, you're great. So then we're going to talk about interior, exterior, and central angles. So you actually explained one of them earlier,
Mhm.
and that was, of course, our exterior angles here. So whenever you
Mhm.
showed us your example, you gave us the label of course, the triangle, and then we found the degree of the
Mhm.
outside angle. So you
Yeah.
called that the exterior angle. And so if
Mhm.
we know what the exterior is, we actually kind of have a hint in our others. And
Mhm.
so we'll go ahead and cross out exterior. So interior has a little hint for us, and that's in, meaning inside the shape, interior.
Mhm.
And then we'll cross that out. So then the only one that's left is central. But whenever I think of central,
Mhm.
I think of center right in the middle of town. Of course, racetrack season,
Yeah.
very, very busy. But central would be, of course, the center of town and the center
Yes.
of our shape here.
See, I kind of think of like when you're hanging up an image, you want it to be centered, like centered right in the middle. So thinking of like this image, or the shape, center, and how we were determining the radius earlier.
Mhm.
We seen that the center was actually 0.0, That means it's directly in the middle. So,
Right in the middle. Absolutely.
but
That,
both good ways to think
yeah,
about it.
absolutely. So, what is a plane when working with shapes, Kim?
So, thinking about a plane, we've learned, a couple of our team teachers, we learned what platforms were, the base, or we also call it. So a plane is just working with a shape that has a flat surface. So we see that we have, let's go ahead and just look at these bottom images first.
Okay.
We see that we have like a cube and a rectangle. We see that every corner and edge of the shape is flat, correct?
Mhm.
Or, thinking about this triangle here, this may be a flat surface, but not all the edges and vertices. A triangle's not flat as if,
Mhm.
a rectangle would be as well. But we
Mhm.
also have something, different called a plane of symmetry. And we talked a little bit, about symmetry and everything. So thinking about symmetry, we know that symmetry divides a solid into two identical parts, almost as if like a reflection of each other.
Mhm.
Each part is a reflection of each other, actually. So we see that when we're dividing this rectangle, we're actually getting two squares, or dividing this, we get two triangles. As well, here we would actually get two triangles as well.
Yes.
So it's pretty simple. We just know that a plane is actually just any flat surface.
Yes. All right. Now taking a look at the tetrahedron, octahedron, and isohedron. Iosahedron?
Yes.
Still don't know how to say it. That's okay.
Yeah.
So let's just take a look, of course, at this first one here on the left-hand
Okay.
side. And let's start by counting. So 1, 2,
Of
3,
course.
4, 5, 6, 7, 8. So what animal do we know of that has 8 tentacles?
Octopus.
The octopus, that's right. So
Yeah.
whenever we see a shape that has those 8, we're going to think of
Mhm.
course, our octahedron.
Mhm.
And then, well, we can't spell it, but we can say it, which is more than we can
It's
say
all
about
right.
the isohedron. Iosahedron?
Yeah.
Yep, that's okay. So then, of course, something that we see here is that with this shape, this triangular prism, it's
Mhm.
actually a tetrahedron, and it actually has a T, so it gives us a hint. So this is the
Yeah.
tetrahedron. And
I
then
love that you pointed out with the octahedron that octa stands for like octopus, with 8 legs.
uh-huh, yeah,
I
I
just think it
love
was
coming up
funny.
with little things like that, just making those connections. The more connections, the
Mhm.
more real you can make it. I think it makes it the
Yeah.
easier to remember. And then the
Definitely.
iosahedron, I don't know how many sides this has. I knew it one time, and I want to say it was like
I think it was
16.
16.
I think something like that,
Yeah.
but it was definitely more than 8 and definitely more than 4. So through the process of elimination, we would know that this one here is, of course, our iosahedron.
Yes.
And my pen is just not working for me, but that's okay.
It's all right. Yeah.
All right. So then taking a look at our next one. So we know the area is, of course, the area inside of an object. And we know the formula for that. It's A equals length times width. So area equals length times width.
Mhm.
But what about perimeter? Can you help me explain that?
Of course. Well, the perimeter is, if you think of a fence, it's the boundary that surrounds a shape. Or,
Mhm,
if we have area and we have a backyard, right? And we put up our fence, the area would be everything that's in the backyard, all the footage and everything, square
mhm.
footage in the backyard.
Yes.
But, think about perimeter. Thinking about movies, we think about surround the perimeter. They're actually
Yep.
talking about the outside of our area. So like the
Mhm.
outside of our backyard.
Yes.
But it's the length that outlines a shape or, a space, I guess. But it's also the sum of all the sides of that space. So if we did have a fence around our backyard, typically we have, a fence and it normally has 3 to 4 sides. We would just add up all of those sides and that would give us our perimeter. So
Okay.
looking at this shape, I just wanted to point out in the middle here that that's actually going to be considered area, and it
Mhm.
has nothing to do with perimeter because it's inside the shape.
Okay.
Um, but looking at the outsides, we just want to add up those 3.
Mhm.
So 48 meters plus 69 meters plus 82.3 meters would give us 199.3 meters, and that would be our equals P, our perimeter.
All right.
And like you said, if we were to find area, it would just be the length times the width.
Absolutely. All right. Well, that one's kind of easy. So, what is the difference between centimeter squared, and centimeter cubed? Now, I know whenever we were thinking of the equation, we just kind of decided on centimeter, but we know that it could be, of course, anything feet, inches, any of those. So we know,
Hmm.
of course, that centimeter, we're talking about dimensions. So with the
Of course.
dimensions, we know, of course, that everything is a one dimension. So one dimensional shapes
Hmm.
are only measured in one direction. So those are going to be considered like our lines. Whereas
Hmm.
two-dimensional objects are shapes that are flat, like circles and squares. And then our three-dimensional objects are going to be like us. We're three-dimensional,
Of course.
or like a 3D movie. So shapes
Hmm.
that have depth to them, like cubes or spheres. Um,
Hmm.
and
Of course.
with the centimeter, I just wanted to point out that there is like an understood 1 here. Okay.
One right there. Of
Mhm.
course.
So then we can talk about the different types of rigid motion. So we have a couple of different
Hmm.
types. So let's just briefly kind of go over those. So we have the translation here,
Okay.
and what we can think of that is so we have this shape here, the triangle, and we're just going to
Hmm.
slide it this way.
Mhm.
It doesn't change the shape. It's not larger, it's not smaller, it doesn't rotate. Whereas
Mhm.
whenever we rotate, we think of right here, I guess you probably can't see too well with my blue pen, but that's okay. So we take this point here and we see that it
Mhm.
turns to here, and it just turns. It rotates.
Yes, of course. So
Um,
there's no sliding within that. It's just turning.
Absolutely. So with the reflection though, you could almost think of a mirror right here. Whenever you look in the mirror, you see yourself, but it's a reflection
Mhm.
and it's just flipped horizontally.
Yeah.
So if you have a freckle on this side, it's going to be, on this side, on that side. So it's a little tricky at
Yeah.
first, but, and it can be horizontal or vertical. For this one,
Mhm.
it is vertical. But then we
So like the y-axis.
the y-axis. And then the glide and reflection, it could also be a slide and flip because it first, of course, slides. It's the same shape,
Mhm.
same size and everything. It just moves down some, and then it goes over the
Yeah.
x-axis or the horizontal line. Same shape, it's just flipped over that line, that axis.
So it's really just a mixture of translation and reflection together, just glide
Yes.
reflection.
hmm
Makes a lot of sense.
Yeah. So then we have, of course, how would we determine the height of the cliff? Could you go over that one?
Yeah, of course. This one was a little bit tricky for me because had to like do a lot of converting before, trying to solve this problem, which is good because we always want to label what we need to do first. So we know that we have 2 feet of ruler. She has 2 feet of ruler down here, and that's our little image that we kind of base everything off of. We know we have 1.5 inches marks apart, and we know she's a quarter a mile away from the cliff, and we're trying to determine the height of the cliff. And what we're going to do here is simply just do cross multiplication. And a lot of students may get confused. They might think that we're trying to multiply the numerators together or multiply denominators together. Because I remember as a student, going through class, I actually thought of that. I thought that's what we were supposed to do, but never really understood, what the cross multiplication is. So just making sure we clarify that.
Mm-hmm.
But back to the converting, we see that we have 1.5 inches. Well, we're trying to convert everything into feet to find height because when we're talking about height, we're not ever talking really about inches. We're talking about either feet or miles.
Mm-hmm.
The easiest one here would be height. So we're converting 1.5 inches divided by 12 inches, and we would get 0.125 feet. And then we're converting the quarter of a mile, that would equal 1,320 feet. And so doing that cross multiplication, we would have 0.125 feet multiplied with 1,320 feet, and that would be equal to 2 feet of the ruler multiplied by h, which just stands for the height. So we would get 165 equals 2 times h. What would we do to get, h by itself is divide everything by 2. Well, 165 divided by 2 would give us 82.5, and all we would have left on this side is h. So our height would be 82.5 feet.
Mm-hmm.
So that's all we really have for that one. It was a little more, when you're reading it, you're like, oh no, I don't know how to do this, but you really do. It's pretty
Mm-hmm.
easy.
Absolutely. All right. So we can jump over to, well, I guess that's all we had. I thought we had one
Oh,
more. That's okay though. I guess that's the conclusion of our final team teach. It's been great working with you this semester and I've really enjoyed it.
yay.
All right. Well, thank
Yay.
you,
Thank
Kim.
you.